In this short video, we'll talk about Atiyah Hodge Theorem. So first of all, let's state Atiyah Hodge Theorem. So it is as follows. Consider X an affine variety, and a smooth affine variety defined over the complex numbers. Then what Atiyah Hodge Theorem says is that we can find an isomorphism between the usual Rham cohomology of X, seen as a complex manifold, in an algebraic way. This means that we can recover it as the cohomology group of the global sections of the sheaf of differential forms, but considering only the sheaf of algebraic differential forms. In other words, this means that for every closed form, every C-infinity closed form, we can always find an algebraic representative of this closed form, modulo exact forms. So first of all, let me show you some examples to explain why is this always the case. So the first example is the following. Consider X to be the usual complex plane or the affine line minus a finite set of points. Then the Rham cohomology, the first Rham cohomology group, it's generated by these meromorphic forms, dc over c minus each point. And you can see that these forms are in fact algebraic, right? So this is kind of well known. So another example is the following. You can consider an affine curve or an affine variety. For instance, here I am taking an elliptic curve, and you can, well, in order to find generators of the Rham cohomology group of this elliptic curve, we will start by considering the following differential form, which is also well known for people who work with elliptic curves, which is known as the invariant differential. So dx over y is the invariant differential. This differential, it can be seen as an algebraic differential over this elliptic curve, defined by this polynomial equation. This is something very elementary that you can show just using the equation of your elliptic curve. And so this is a global algebraic form defined over X. And it turns out that the Rham cohomology, the usual Rham cohomology, is generated by this global differential and X times this differential, okay? And both are algebraic representatives. The last example that I will show you is a bit more involved. That is the following. Consider Pn, the projective space, minus an hypersurface given by some polynomial, homogeneous polynomial f of degree d. Consider then this standard top form omega, which is defined, well, just in this way. It is the alternate sum of this variable xj times this differential, which takes all the differentials of all variables except by the one that is in the jth position. Okay, so as I said, the Rham cohomology group is generated by these algebraic forms, which have pole along this hypersurface that we have removed. And these PIs are polynomials, homogeneous polynomials of this degree. Okay, so Now I will explain the proof of Atiyah Hodge theorem, and it will have several steps. So the first step is to reduce the proof, to reduce the theorem to a purely analytic statement. So in order to do this, we first need to use Hironaka's resolution of singularities. So this theorem allows us to embed X, which is an affine variety, inside some smooth projective variety, X bar, which is thought as a completion of X. And furthermore, we can assume that this completion is done in such a way that Y, which is defined as the divisor at infinity, the divisor that we add to X in order to complete it, is an ample normal closing divisor. So this means that it might be singular, but the singularities that can appear, they are not so bad. They are as good as possible. And more precisely, this means that when we look at each singularity locally in a small neighborhood of the singularity looks like a product of hyperplanes. Okay, so we are in this setting now, and in order to pass from the algebraic setup to the analytic setup, we will use Serre-Gaga correspondence. This is why we needed to compactify first. So how do we use Serre-Gaga correspondence? In the following way. So first of all, our statement is a statement about the cohomology of the global sections of algebraic differential forms. So we can see these algebraic differential forms, which are defined over the affine variety X, as some other algebraic forms defined on the completion. This is possible after pushing forward the differential forms on X to X bar. So once we have this sheaf defined over X bar, which is a smooth projective variety, we can use Serre-Gaga correspondence to obtain the isomorphism between the global sections of this sheaf, which is exactly the zero cohomology group, with the global section of its analytification. So note first that in order to use Gaga correspondence, we need a coherent sheaf. And this is not necessarily a coherent sheaf. This is not, in fact, a coherent sheaf. But it is a limit of coherent sheaves. And that's why we can use Serre-Gaga in this case. So the analytification of this sheaf is not very difficult to see, that it corresponds exactly to the sheaf of forms with pole of arbitrary order along Y, right? Because this is exactly what means to be an algebraic form defined over X bar minus Y, right? That's exactly being a rational form with poles along Y, right? And when you translate this to the analytic setup, you will get a meromorphic form with poles along Y. This is exactly this. So we have this isomorphism given by Serre-Gaga correspondence, and in fact we have the same isomorphism for each cohomology group, not just the zero one, but for all of them, right? In particular, this implies that the Q cohomology group of this sheaf will be zero for Q bigger than zero, right? And this is true because the Q cohomology group of the sheaf of differential forms over X is zero, and that's why, because X is an affine variety and omega K is a quasi-coherent sheaf over X. This is a theorem due to Serre. So in consequence, In consequence, this second equality implies that this sheaf, this complex of sheaves, they are all acyclic. They are all acyclic sheaves. And so the cohomology of the global sections of algebraic forms, which we know is isomorphic to the cohomology of the global sections of these meromorphic forms with poles along Y, since this complex of sheaves is acyclic, we know that this is exactly the same as the hypercohomology of this complex. Now we have reduced one part of the isomorphism of Atiyah Hodge theorem to a purely analytic statement, right? And now we want to reduce this to a statement about hypercohomology groups. So in order to do this, we just need to state the usual de Rham cohomology in terms of an hypercohomology. And this is simple, since we know that by definition, the usual de Rham cohomology is just the cohomology of global sections of the infinity forms defined over X. And since these sheaves are also acyclic because they are fine sheaves, this is again the hypercohomology of this complex of infinity forms. And so the only thing, we have reduced the Atiyah Hodge theorem to prove the isomorphism between these two hypercohomology groups, which are defined over the analytic topology of X bar. And so we just need to show that these complexes are quasi-isomorphic. So we want to show that this is a quasi-isomorphism of sheaves, of complexes of sheaves defined over the analytic topology of X bar. So the second step is to reduce this to the proof of this quasi-isomorphism to a lemma just about meromorphic forms defined locally on germs of neighborhoods of points of X bar. So let's proceed to show the quasi-isomorphism. So around any point in X bar, you can consider a small polydisk contained in X bar. And we will separate the analysis in two cases. So the first case is when X is not in Y, it's not in the divisor at infinity. So in this case, we can assume that the polydisk is small enough such that it doesn't intersect Y. So in this case, if we look at the complex of meromorphic forms with poles along Y, restricted to this polydisk, we will see that this is exactly the same thing as the complex of analytic forms over delta. And so this complex is quasi-isomorphic to the complex of infinity forms, and this is just because both are in fact resolutions of the complex, of the constant sheaf C defined over delta. In the case where X is a point of Y, we can assume that we can take a neighborhood which is a polydisk given, which is isomorphic to some to the disk power to n, and we can give to it some coordinates in such a way that the intersection of Y with this neighborhood is the zero locus of a product of variables. This is exactly the definition of Y being a normal crossing device. So in this setup, we see that the K-cohomology group of the global sections of the complex of infinity forms restricted to delta, to this polydisk, is exactly the same thing as the Rham cohomology of delta minus Y. And in this case, it's easy to see, since we're identifying delta with the usual unitary polydisk, minus this product of variables, it's very easy to see that the Rham cohomology group of this set is just generated by these forms dc1 over c1 wedge until dc iq over ciq, where I1 and IQ are between 1 and R. Okay, in particular, we show that the usual Rham cohomology here around this point X is generated by these forms, which are in fact algebraic forms. So this is showing that when we look at the natural map between this complex and this other complex restricted to this other delta, we want to show that this is a quasi-isomorphism. And this is exactly the same as showing that the sheaf of cohomology of this complex is isomorphic to the sheaf, the cohomology sheaf of this complex. And in order to show that, it is enough for us to show that the cohomology pre-sheaf are in fact isomorphic, right? And so what we have in the right-hand side is that the cohomology pre-sheaf is given by this kind of a space, which is generated by algebraic forms. And so we know that the cohomology pre-sheaf in the left-hand side at least is mapped surjectively here, because each cohomology, each element in the cohomology here will have a representative coming from the left-hand side, which will be a meromorphic form with poles along Y, right? So the only thing that we need to prove now is that this map is in fact injective. And so we're reduced to the following lemma, which says that take omega any closed meromorphic forms defined over a polydisk delta as before. Assume that this omega is holomorphic in delta minus Y, which is identified with this set. And furthermore, assume that this omega goes to 0 under this map. This means that it is 0 in the usual Rham cohomology. Then we have to show that it is 0 in the previous cohomology. So in the cohomology induced by the complex of meromorphic forms. That means exactly that there exists a meromorphic K-1 form defined maybe in some smaller polydisk contained in delta around X, such that this meromorphic K-1 form is holomorphic outside Y, and the omega is exactly delta of this eta. So now the third step is to prove the previous lemma. So let's do this. So the first thing we have to do is to take this form omega, and we will write it in the following format. So we will write it as, we know that it is a meromorphic form, so we can write the polar part downstairs, and upstairs we can consider only holomorphic forms. Furthermore, we can separate the holomorphic part in two parts, one mu1 and dCn wedge mu2, in such a way that mu1 and mu2, they both are independent of dCn. By this, I mean that the expression of mu1 has to be of the form some holomorphic function times this kind of differential dci1 until dcik, because it is a k form, but with these i1s until ik between 1 and n-1. So dcn never appears here. Also for mu2, we have a similar expression with holomorphic functions, but the only difference is that now we're considering only k-1 differentials, because mu2 must be a k-1. Okay, so we can write omega always like this. So consider now this function C I1 until ik as a holomorphic function defined as the formal primitive or the formal integral of these holomorphic functions with respect to the last variable, to the variable Cn. So it will be again a holomorphic function, possibly defined on some smaller polydisk, but it's again a holomorphic function. So once we have integrated this formally, by formally I mean that you take the power expansion of this holomorphic function and you integrate it as a power series, right? So this is why you can always do this. So using all these new holomorphic functions, we can produce another k-1 form, which we call nu. And this nu is defined in this way. And so we see easily that if we subtract from omega the differential of nu over the polar part, we will get a meromorphic form which is independent of dCn, because we will cancel this part of here, of nu2. And so, since omega is delta closed, this other form is also delta closed. And this implies that since dCn never appears here, also Cn must be, I mean, the holomorphic functions appearing in the expression of omega and minus this exact part also must be independent of his Cn. Otherwise, there will appear some dCn when you take the delta of this thing. And that's impossible because the delta of this is 0. And so with this procedure, what we have shown is that in modulo the delta of some meromorphic form, meromorphic k-1 form, we can always remove the dependence on the last variable, on Cn, right? And so we can iterate this process and remove also the Cn-1, Cn-2, and we can continue until removing Cr+1. And so we will get some meromorphic form, maybe defined on some possibly smaller polydisk, in such a way that when we remove this meromorphic form, we will get something that is independent of dCr+1 until dCn, and also independent of Cr+1 until Cn. So this reduced the proof to the following claim, which is exactly the same lemma, but in this particular setting, right? So this claim says that whenever we take a meromorphic K form, now defined only on dr, so we're just thinking omega as a form defined depending only on the first r variables, such that it is holomorphic outside the locus, the zero locus of the product of the variables. This means that it's holomorphic in D minus the origin power to r. And furthermore, we know that this form omega is a closed form in the usual Rham cohomology. Then there exists some meromorphic k-1 form, again with poles along this product of variables equal to 0, such that omega is delta of it. This is what we have to show now. Finally, we have to prove the claim, and the proof is just by induction. So first, the case where r is equal to 1, we have just one variable, This case is very simple because we're just considering a meromorphic form in one variable. And so when we look at the Laurent expansion of this meromorphic form, the only part that can be giving a problem or cannot have a primitive or cannot be integrated is the part with corresponding to the coefficient -1, the part the coefficient -1 over z. And since we are assuming that our form is 0 in the usual Rham cohomology, this part vanishes. It never appears. So this case is very simple. So assume now that we have more than one variable. So as before, we can write omega in the same format, mu1, mu2, and now mu1 and mu2, they are depending only on the first R variables, but they are independent on DCR. So take these holomorphic functions. We can take the power series expansion of this holomorphic function with respect to ZR. And now consider these holomorphic functions being the primitive of these B functions minus the part that might give some residue, right? So we remove of this power series, we remove the term corresponding to L-1 because once we divide this by this polar part, this part will give some residue. So once we remove this won't give some residue, and so we can formally integrate it, and again we will get some meromorphic form or meromorphic function. So with these meromorphic functions, we will produce this meromorphic form psi, phi, and as before, we just remove this meromorphic form, and we will be able to write this in this format. It will be some chi1 plus chi2 times dCr over Cr. And here, chi1 and chi2, they will turn out to be independent of dCr and also of Cr. Furthermore, they will be closed forms, closed meromorphic forms. And finally, by Counnet's theorem, it will imply that since this is exact in the Rham cohomology, each of these closed form also must be exact in the Rham cohomology. And so the theorem will follow by induction, because these meromorphic forms depend now just on R-1 variables.